Welcome back, my structural analysis friends. In the last couple of videos, we've been talking about virtual work, and we've analyzed systems such as trusses and shown the method to be able to use the methodology to find our deflections. In this video, we're going to turn our attention to beams. Okay, and the beams it's a similar concept that there will be a real system and a virtual system, but the equations change a little bit, and so I'll show you how to do beam analysis using virtual work. So without further ado, let's get started. So the deflection of beams, we're going to go through some basic bending theory like what we've done in some of the other videos when we first started talking about deflections of beams. And so I'll walk you through the methodology, and again, the challenge here is that we have to come up with a virtual system for finding the deflection that we're after. Okay, and so as you might suspect, there's going to be a unit load involved, and then we'll do a derivation based off of that. But we'll show you what the equations are here in a moment. All right, so here's what we have. We have a simply supported beam with some arbitrary loading on it. So I got some distributed load. I've got a force, a vertical force in this guy, and we're going to examine a single element here that has a width of dx and is located at position x along the beam. Okay, so what we're going to do is we're going to basically, like we did with our virtual work derivation a couple of videos back, is we're basically going to tally up all of the work energy that each one of these little elements does along the length of the member. Okay, so this would be our real system. With the real system and the real loads, we should be able to draw shear moment diagrams and be able to come up with generalized equations just like what we've done previously. That part doesn't change. Okay, so that should be no surprise. Our beam has a length L. We have our delta at B, so for this particular example, we're going to set up that we're looking for the displacement here at B. Okay, now notice it's not in the middle, it's not at the left, it could be anywhere, but we arbitrarily chose a point B, so you would have to know its position according to that, and so you would solve for all of the internal effects of the beam and the energy related. Okay, the virtual system, and just like in trusses, remember when we did trusses, we said that the virtual system that we're after has to do with the deflection or the effect that we're interested in, okay, with a unit load applied at that point. So suppose I want the displacement at point B. Well, then my derivation is no different than what we did with trusses. I put a 1 unit load, so in this case 1 kip or 1 kilonewton or whatever, I put a unit load at my point of interest in the direction that I want. Now, in a flexural theory case, we don't often do an axial load on this guy, all right, because we assume axial deformations are very small. Okay, but for vertical, this one works out pretty well. Okay, so again, here's my incremental element, and we have a position X, and I'm putting my unit load here at B, wherever B is located. Okay, so it's exactly the same as what we did. So we know from our derivation before that when this beam flexes, we're going to get some sort of deflected shape or elastic curve that bows this thing down, and as a result, this beam is going to have moments on the end of it. Okay, so what we do is we basically say that, all right, if this element is small enough for an arbitrary element in here with a 1 kip load, it flexes such that, if we started out with assume a rectangular cross section, this point across here is the neutral axis, okay, and then this represents the strain. The bottom wants to get longer and the top wants to get shorter as we look at the slice of the piece, right? It turns it from a rectangle slice into kind of a trapezoidal shape. And if dx is very, very small, then the moment that's induced on this member is matched by a moment that's induced on this. Now, that's not exactly true, but we're assuming dx is tiny. Okay, it's infinitesimally small, and so the difference in those two values should be negligible, but that's the moment that's happening on this, and that's why this member is compressing at the top and growing at the bottom. Okay, the amount that it compresses then is of this incremental element is some d theta. It's the amount of the total angle change of this particular beam, all right? And so we know from our previous calculations and derivations back in our double integration method that d theta is going to be equal to m over ei dx. Okay, that the first derivative of the slope is m over ei dx. So that's the same thing that we did in the double integration method, this equation here. Okay, so what we do is, so this is for displacements, for finding delta B. For displacements then, the internal virtual work of this is going to be equal to the work on this particular element is going to be equal to the moment multiplied by the rotation that it goes through. So it's going to be mv times d theta will be the incremental work associated with this piece. Okay, so if we know that then that the change in the d theta is the real moment over EI dx from our basic governing differential equation definition, then I can solve for the incremental work by substituting this guy into this equation. And what you get is now for that little sliver, this dx element up here, it is the virtual moment times m over EI, where m is the real moment, multiplied by dx is the work that's done on this little piece. Okay, and so then if I want to add up all of the energy of all of the elements on the beam, all I do is I integrate from L to 0. Okay, and that's what we do. So the internal work energy of this beam is the integral from L to 0 of mv over m over EI dx. All right, and then once you have that total energy calculation done, then you can come in and do, we know that the external work is 1 times the delta that we're after, and so that's our virtual external, and I can set this equal to this, which is what we did, and so that 1 times delta equation looks just like what we had in trusses, is now the integral from L to 0 of mvm over EI. Now again, m is the real moments from the real loading. The mv is the moment associated with a 1 kip load or 1 kilonewton unit load here. Okay, so this is what you would get for the displacements, to find the displacement equation. All right, now if we go through, we can also, the other unknown in beams is often the rotation, and so we can play the exact same game. Okay, so I've got my beam, here's my point B, and say we want the rotation at B. I'm going to apply a unit moment this time. Notice it's not a force, it's a moment. I chose to go counterclockwise positive on this. Okay, and we'll apply a unit couple at that location. And so the work energy, if you go through the formulation for this, it turns out that the total work energy for all of the elements ends up being the exact same formula. Integral from L to 0 of mvm over EI. Now what's changed is this guy. The formula is the same, but the mv's are different. Okay, and then times dx, and you integrate that, and that's the same formula, and then the rest of the step is exactly the same. Except now the virtual external work is my unit moment times its rotation. Okay, and so I set this equal to my integral, and then now we've got a 1 times the theta. So I can get the rotation doing the exact same methodology, it's just that the load now changes. You put a moment on instead of a force to get a rotation. All right, so let's try a couple and kind of give us some practice on this and see what we can come up with. So what I have is I have a fairly simple beam here. It's a cantilever beam that is fixed at the right end and has a unit load, triangular distributed load acting on it. It's 0 out at the cantilever end, and it climbs up to what would be an amount W here. So the equation of this load is W over L by X, or times X. All right, so at any X value, at X equals 0, it was 0. At X equals L, it was W. And so this becomes the function associated with this line. And we'll need that because we've got to come up with a generalized moment equation. Okay, so if we go through and we kind of look at this, we can come up with our generalized moment equation on this by looking at, in fact, let's just sketch that in here real quick. That if we look at an incremental slice of this thing that's X long, okay, if it's X from here to here, then this is Wx by L is that amount. Then when I cut here, there's your moment at X, and then you've got your shear and your axial also, but we're not too worried about those. Okay, and you can see, but this moment at X is what we need. Okay, and that will be the moment, the real moment that's on this. So my M as a function of X, this is that generalized moment equation stuff that we've been practicing. Okay, that the moment at X then is, you know, if this is all distributed load, I take the area of the load, so 1/2 of X times W X over L, that's the first set of terms here, and then multiplied by the resultant of that triangle load is acting at 1/3 of X away from my point here. So that's why there's a 1/3 X there. And if I do that, my moment then is minus Wx cubed over 6L. Okay, and that's my real moment for all values of X. So we got to use these generalized equations to be able to do virtual work. Okay, now suppose that we are after finding the displacement and the rotation at A. Okay, we're going to assume that EI is constant in this. It doesn't have to be. EI can actually vary with X in this. This is one thing that's cool about the virtual work calculations, is that E can vary with position, as can I, and so if I have these written as functions of X, then I just plug them into the integral and I can evaluate. Okay, so what we're going to do is, in order to find, say, let's start with the slope of this, we said we're going to apply a unit moment to the end of this thing. Now I chose to put a moment on this clockwise, no particular reason. I just I went clockwise, and so if I put this moment on, we would expect this beam to curl upwards. Now, if we do our energy calculation and we find out that it's negative, then we'll know that what we did is backwards, because this is the arrow that dictates the direction of the slope. Okay, and you can see by looking at this, clearly it is going to be backwards. That load is going to bow this beam down. You can see that. So this guy, we should get a negative number on our energy calculation when we do it. Okay, so this becomes my real system, or my virtual system. Okay, and again, we're looking at an arbitrary element here at position X. And so if we cut this guy at X, this is the free body diagram that shows up at the cut. So here's my cut line on here, and so I've got the moment at the left end of 1, and then I put my sign convention for my internal forces. So my internal virtual moment is going to be counterclockwise acting on that face of it, and that's the free body diagram. Okay, when I go through and I do that, what will happen is then basically just like you did before, we're going to solve for that virtual moment. This called as, I think, M1X. Different books call it different things, but this is the virtual guy. So this is my MV. So M1 on this is going to be then, sum of moments at this point is going to be M1X minus 1 all equal to 0. So M1X is equal to 1 everywhere. Okay, and that's on the interval of 0 less than or equal to X less than or equal to L, because that's this free body diagram everywhere for this virtual system. Okay, so then all you do is you plug in to the integral equations. So we know that we have 1 times theta A is going to be the integral from L to 0 of, the first one is my virtual. Again, it was MV in the derivation. It's MX1 here. Okay, but that's my virtual moment. Here's my real moment, all divided by EI, and then times dx, and we're going to integrate that thing. So if I plug in the 2 equations that I had before, this one here for the real and this one here for the virtual, I end up with a 1 times minus wx cubed over 6L EI dx, and we're going to integrate that with respect to L. So it's just a simple integration at this point, that it becomes minus w 6EI L times x to the 4th over 4, and we're going to evaluate that between L and 0. And if I do that math and solve that, evaluate the integral, we get minus WL cubed over 24 EI. And so there's my minus sign. Okay, and that minus sign, again, we said tells me that it's opposite direction to what you had happening here. So in reality, this thing is curling downwards because the moment is, it's opposite of this. So which would be, we assumed clockwise positive. Negative tells me that it's counterclockwise positive is the reality. So then my theta A is just WL cubed over 24 EI, and then it's rotating counterclockwise. So here's my reference, and I just make a little notation that it's going counterclockwise. Okay, and that's all there is to it. All right, to find the displacement, very similar process. This part does not change. This is the real loads, what the real loads are doing in terms of the work energy. Okay, but the virtual system changes. And so now to find the displacement at A, I put a 1 kip load at A. In this case, I assume down is positive. So again, if we get a backward sign, it will tell me that this arrow is right or wrong. Okay, and we play the exact same game. So here's my generalized free body diagram now. I have 1 kip here. It's a distance of x to the generalized location, and then here's my moment. And so if I sum moments, it's 1 times x, okay, plus m x2, which is my virtual, my new virtual x, okay, and all that equals 0. So then my virtual moment is equal to a negative x. Okay, just doing the math on that. Okay, so then I plug in, just like we did before, now it's 1 times delta A is equal to the integral from L to 0 of the virtual times the real divided by EI dx, and then I can plug in minus x minus wx cubed over 6L EI dx. And so if I evaluate that, that gets me to basically w over 6 EI L multiplied by x to the 5th over 5, evaluated between L and 0. And so the deflection in this is now WL to the 4th over 30 EI is my calculation here. And again, this is positive, tells me that this arrow is correct. The deflection is indeed downward, which is what you would expect. Okay, so be very careful about the signs of this. So that's my delta A for WL 4th over 30 EI. Okay, all right, let's try another one. Okay, one that's a little bit harder. So here I have a cantilever, and we can do the exact same process. Okay, so what we have is we have two different loadings. So it's a simply supported beam with a cantilever on one end. I have a 12 kip load acting down on the end of this thing, and I have a distributed load of 2 kips per foot acting in between. EI is constant, E is 29,000 KSI, I is 2,000 inches to the 4th. Okay, so what we have now though is that I now have 2 different curves that define this moment diagram. Okay, if you remember our critical section or critical location discussion back in those statics videos, that there will be an equation between A and B that defines the moment and a different equation between B and C that define the moment. Okay, so what we're going to do is we're going to first solve for the reactions, and I'm going to assume that we can do that. So I've written those here. AY is 26 kips up, and BY is 46 kips up, and that's the loading that we have, 2 kips per foot. The span is, appears to be 20 feet, or is that 30 feet? Should be, I'll go find the integral. Give me 1 sec. Can't read the, yeah, 30 feet. Sorry, okay. I didn't say the spans and can't quite read it. So this is 30 feet there, and then we have 10 feet for the cantilever. Okay, so for the interval of 0 less than x less than 30, this is the generalized free body diagram. So we're going to cut arbitrarily through there, and this would be the picture that shows up. So again, I'm measuring x off of the left end of this, and so we're going to integrate from 30 to 0, but our free body diagram looks like this. So there's a distributed load, and then we get our internal moment here, and our reaction of 26 kips doesn't change. So with this, I can write the generalized moment equation here. So mx is going to be equal to minus 26x plus 2 times x over 2. So we summed moments here. Here's my moment, my real moment. Okay, and so 2 times x gives me the magnitude of this, and then x over 2 is its location. That's where this term is coming from. And then the 26 kips here is being multiplied by x, and it's a negative moment by my sign convention. Again, I'm assuming counterclockwise positive here. Okay, so the moment, the real moment here is equal to 26x minus x squared is the real moment for that span of the beam. And again, that's only for member AB, which is the interval 0 less than x less than 30. Okay, then we go in, and we're going to do the exact same thing and do an energy calculation on the cantilever. Now, I could choose to go off of the original reference, but because this is an energy calculation, I can also flip the origin, okay, and write my equation. And on cantilevers, I recommend doing that because it keeps your equations much, much simpler. All right, so I'm going to assume that my reference is here, and this time we're going to measure x back to the left. Okay, so I'm going to cut my cantilever off. So what we've done is we have cut, through here somewhere. Okay, and we're measuring x from the other end of the beam. Okay, and so if I write my moment equation for this, here's my internal moment. Now on the left side, this is a clockwise moment positive here, so we're using our beam sign convention. Okay, and then 12 kips acting down. So the moment equation then is going to be a minus mx value, okay, and then minus 12 kips times the distance x gets me the moment that this guy produces about my arbitrary location distance x from the end. All right, so mx then is a minus 12x on this. Okay, so that's our real system and our real moments. We've got those. Okay, now we do the same thing for the virtual system. So since we're looking for the displacement at the tip of the cantilever, so say delta C here, that means my virtual system will be a unit load placed at that point. So we want the vertical deflection at C, so I put a unit load at C in the vertical direction, and I basically resolve the problem that we just did. So I'm going to have an equation through this section, and I'm going to have another equation through this. Now, when you do this, you got to make sure that you keep your origins exactly the same. So on this one, I took x that way, okay, with my reference at the left end. And then the cantilever, I took it from the other end. So you've got to stick to this because I chose that sign convention up above. Okay, you notice that this guy and this guy match, and this one and the one up above will match also. You've got to be consistent there. Okay, it doesn't matter where you call your reference, you just got to be consistent. Okay, so when we do that, when I draw my free body diagram, with a 1 kip force acting out here, the cantilever, the reaction here is 1/3 kip down, and it's 4/3 kips up. And so then I do my generalized section, length of x, 1/3 down here. I get my virtual moment, what we're calling MV1. And so MV1 is going to be MV1 plus 1/3 of x equals 0 when I sum moments. And so MV1 is going to be minus 1/3 x. All right. And then likewise, I'll do the cantilever portion exact same way. And so in this case, it's going to be minus MVX minus 1 times x equals 0. So MV number 2 is going to be a negative x. So exactly what we had before. Okay, and so that should be no surprise. And you can check that because we had minus 12x up here, so it should be a minus 1x here because the loads are factors of 12 off. Okay, once I have that, all we do is we make a table. Okay, and so that's the way we're going to do it. Now, the table's a little bit different, but I'm going to write it this way. I have my segments, A, B, and BC. Okay, I like to write down my origin where I measured x from. And so in this one, I measured from x from A on AB, and I measured from C on BC. Okay, and so the limits of integration on this for A are from 0 to 30. Okay, and the limits of integration on the cantilever are from 0 to 10 because of the way that I defined x. This can change depending on where you did your reference. If I had done my reference at A, I would rederive my equations, and then I would do an integral from what would be 40 to 30, okay, to solve it that way. Like I said, the different ways that you can do it. I just choose to do it this way because I like to have that lower bound be 0. Okay, so then all we do is we write down our real moment equations that we derived. We've derived those. You've seen those. So 26x minus x squared for AB and minus 12x for BC. And then we plug in our virtual ones that we came up with, and that this AB one was minus x over 3, and then the cantilever was minus x. Okay, and then all we have to do is plug into our integral as we start to kind of look at this. So I have 1 times delta is going to be equal to the integral from L to 0 of mvm over EI dx. Now, the difference here is that we've broken this beam up into different lengths. So we're going to split this guy. So instead of going from 0 to 40, we're going to write our equations for the energy calculations as a sum of the pieces. Because again, I'm just looking for the energy in AB plus the energy in BC that's taken here. So we're going to integrate from 0 to 30. So the 0 and 30 came out of what you set your limits at here. Okay, and then I plug in this times this into the equation, and that's what you get. And then the next one is from 0 to 10. So those are my limits on my integration from 0 to 10, and then I have minus 12x and minus x become that guy. Okay, so if I go through, now you just do your calculus and some algebra, and if I evaluate the integrals just like we did before, all I'm going to do then is basically do 1 times delta C is going to be equal to 6,000 kip squared feet cubed over EI. So watch the units on this, okay, because again, most often you have I's running around in this, okay. And so it's a minus 6,000. And what did we say that the minus indicated to us? Minus tells us it's opposite to what the virtual load was doing. So if I come back and look at my picture, the negative tells me I assume down positive. It means that this tip is actually rising up. Okay, and that should seem reasonable, right? I have a real heavy load pushing here and a real small load pushing down. So this guy is going to push it, and this guy's going to go way up, and then the little load is going to push it down, but not enough to make it go past 0. Okay, so that seems somewhat logical, and that's what's happening with this negative sign. Okay, so it's opposite of what we assumed. Okay, so then I can plug in my calculations. So minus 6,500. I have my inch to feet conversion, and there are 3 of them, so that's why it's 12 cubed. And then I have 29,000 KSI, and I have 2,000 inches to the 4th. And when I do this, my deflection will be 0.194 inches negative. Okay, and so what the negative means is it's opposite what I had. So delta C is moving 0.194 inches upwards. Okay, that's what the negative sign here was telling us. Okay, and that's the method of virtual work for beams. It's pretty easy. Again, all we're doing is we're tallying up the energy of all of the pieces. Okay, in trusses we did it member by member. In this beam, this last beam problem, we did the cantilever piece and then I did the main span piece. And all we're doing is an energy calculation for the virtual moments and the real moments on each of those pieces and then doing our computation accordingly. Okay, and then at the end of the day, it all sums up to be contributing to the delta of the real system. And that's all there is to it. Okay, so I hope that's made sense to you. If you've got any questions, as always, toss us a comment down below and we'll get back to you. And if you found the video useful, please give us a like and be sure to subscribe, and we'll get more coming out. And we'll see you guys next time. Happy engineering.